Hello, everybody. It is my pleasure to introduce the third lecture of Juniha. I was coached a little bit by native speakers before this introduction, how to properly call you. I don't know if that's if my pronunciation is right, but Juni will tell us more exciting things about many different things.
Okay, things are all Lorentzian polynomials. And this time I'm going to tell you about more specific examples of Lorentzian polynomials. And this is joined with two groups of people. First with Chris and second with Jacob Mathern, Carola Mesaros, and Avery Saint-Dizier. The underlined people are graduate students graduating this year. So this is your golden chance to hire these excellent people. So I started by defining the space of Lorentzian polynomials. And told you that they are exactly the polynomials which are strongly log concave. So let me remind you that a polynomial is strongly log concave if it is log concave on the positive orthant. And in addition to that, all its partial derivatives have the same property. But let's think of an alternative scenario. Maybe you are an analyst, and maybe you are interested in Minkowski theory of convex bodies and stable polynomials, and have observed that these two classes of polynomials have similar behaviors, although no one of them contains the other class. So you arrive at this notion of strongly log concave polynomials and consider this family. And you notice that the space of all such things is actually a ball, and it has many other very pleasant analytic properties. And you start realizing that in all your examples of strongly log concave polynomials, the set of monomials that appear in such an expression for the polynomial are all very special, and you try to characterize them. And you stare maybe 5 examples real hard and think about it real hard. And then maybe you arrive at this characterization. Of the support of f, by which I mean the set of monomials that appear in the polynomial f, where f is a strongly log concave homogeneous polynomial. And the condition you discover is that of M convexity, which says that whenever you have two monomials, maybe alpha and beta, and for any direction I, which favors alpha, there should exist another direction j, so that if you drag alpha and beta toward each other one step, then the two new points is again in the support of your polynomial. So that is a strange condition, but it is what it is. So maybe you take this to your friend who is an algebraist. And you ask her whether you have seen this condition. Probably the answer will be no, but she will immediately point out that this EI minus EJ is a root. In type A. And then she'll try to sell you this idea that there are these things called root systems, called A, B, C, D, E, F, G, and so on, which governs all the symmetries of the universe, and so on. And she also points out that the weight polytope that they care about satisfies your convexity condition. And then she will soon start speaking about something you don't understand, so you walk away. But you just note in your journal that like A, B, C, D, E, F, G are important, something like that. And then you take this condition to your polytope friend and ask whether he has seen this condition. And then he will point out that your condition with many quantifiers, 4 quantifiers, is in fact equivalent to the statement that the convex hull of the support being a generalized permutohedron. So you ask to him what is a generalized permutohedron, and then he's going to tell you that generalized permutohedron is a deformed permutohedron. So of course you ask him what is a permutohedron, and then he will tell you that it is the convex hull of an orbit of a general point under the action of permuting its coordinates. So you take this description back to your algebra friend, and she'll immediately point out that the group of permutations is a Weyl group of type A. And she'll going to define for you what generalized permutohedron must be in all types. And then maybe you take this condition to your combinatorics. And then she's going to tell you that your condition is exactly the condition that support of F being a discrete polymatroid. So you ask her what is a discrete polymatroid. And then she's going to tell you that it's just like matroid, except that you allow multisets in basis. So you ask her what is a matroid. And then she's going to maybe show you a small graph and show you how to exchange edges in a pair of spanning trees, and maybe show you a picture of Fano plane or something like that. Okay. And then you go to a library and notice that there is exactly one book which mentions both matroids and root systems. So this is the last book written by the great Gelfand, titled Coxeter Matroids, written with his co-authors Borovich and White, that absolutely no one before you have checked out. You're the first one who is reading this book in your institute. And the authors of this book will try to sell you this idea that what combinatorialists call a matroid is in fact matroid of type A. And of course, there are matroids in all types. Okay, so now you are brainwashed enough. So you ask yourself, I mean, what did I do wrong? I simply started from this condition of log concavity. And then I ended up in type A world. I didn't make any choice. And there's nothing really type A about log concavity, to my eyes. So I don't really know what root systems are, but my guess is that, well, first of all, there is nothing type A about logarithmic concavity, but I think this type A phenomenon we have discovered here actually comes from our choice to its special class of functions, which is a homogeneous polynomial. So I don't have a very good idea of what the corresponding analytic theory might look like in other types. So instead of telling you about vague guesses in that direction, let me give two examples. In type A, so two manifestly type A examples of Lorentzian polynomials, or strongly log concave polynomials. So these examples are clearly type A, and I think they have clear analogs in other types. So by thinking about these two examples carefully, we may arrive at the corresponding analytic theory in other types. So the first comes from graph homomorphisms. And I'll tell you later why this is so type A. So let's start from a graph. Maybe G. And let me view it as a pair of sets, edges and vertices, where the set of edges is a subset of the product of vertex sets. And let's agree that a morphism from one graph G1 to another graph G2, say V, is a set map from V1 to V2 such that it maps E1 to E2. So just for fun, let's fix one example. Maybe I have one graph on 6 vertices and 9 edges. And maybe I can map it to a triangle with vertices 1, 2, 3 by sending this to 1, 1, 2, 2, 3, 3. So that is a homomorphism between two graphs. And of course, this generalizes familiar notions like vertex colorings. So when the target is a complete graph, this is a number of ways to properly color your vertices. In this case, it's a 3 coloring of the domain. And let's make this graph into a matroid by taking the set of all spanning trees. Of course, you can do this for both G1 and G2 and get 2 graphic matroids. So in such a situation, I think it's completely normal for a human being to feel the inner desire to make sense of this so that M is a functor. Right? That's the modern trend. So you want to know what this guy must be. So let me bluntly give you a definition first. So let's say you have a matroid M on M, and maybe another matroid N on N. And let's say that a morphism from M to N is a map from M to N, written by the same letter, such that rank of M over S2 minus rank over M over S1 is always larger than rank over N over phi S2 minus rank over N over phi S1. For all S1, S2 in M, where rank M over S is like yesterday, the maximum cardinality of S intersected with a basis. And same for N. So for those of you know, this notion is nearly identical to the notion of strong maps, except that I'm not dealing with any imaginary elements or things like that. And then you check that it does what we want to do. So for example, if you have a map from G1 to G2, the induced map between the edges gives a morphism from mg1 to mg2. And secondly, if you have a finite set of vectors, maybe in some vector space f to the d1, and if you have a linear map from fd1 to fd2, then you have a map between the matroid of A, collecting all the bases of the vector space contained in A, to the same matroid but for the image of A, keeping the labels. The idea that I want to tell you now is that this is really a convexity condition, convexity in our discrete sense. I mean, it is not very clear why this can be interpreted as a form of discrete convexity, but I think this is because we are all not very well trained in this notion of discrete convexity. So let me try to convince you why this is a notion of convexity. But this, if you admit this as the correct notion of morphism, then you begin to meet examples that are quite mysterious. So this is an observation due to Edmonds, which shows you that morphism between matroids can arise in quite unexpected circumstances. So for example, if you have a graph in, say, some surface, maybe you have a cellular graph, G, a surface, then it happens that the dual matroid for your graph G canonically maps to the matroid of the dual graph, where the first star is the matroid duality, and the second star is a geometric duality where you use S to construct geometric dual to G. And on the underlying set level, this is a bijection between their edge sets between G and G star. So for example, if you triangulate torus in a minimal way using K7, then somehow the dual of K7 canonically maps to the graphic matroid of the incidence graph of the Fano plane, because this is how K7 triangulates the torus.
So it's not isomorphism.
this is not an isomorphism. It is a bijection between the ground sets.
So if S is a plane, then it's...
That's right. That's right. When S is a plane, it is an isomorphism. So somehow this kind of morphisms detects this, this sort of topological information. Okay, so let's see. So let me remind you what we did yesterday with this Potts model partition function. I told you that this function is Lorentzian whenever the parameter q is in between 0 and 1. And from that, we have derived that the independent set generating function of M is Lorentzian, simply because this is a suitable normalized limit of the former. And from that, we have derived purely enumerative inequalities like this. Yes. So where fkm counts the number of k-element independent sets of M. Oh. So for example, when M is our favorite Fano plane, then F, let's see. So the inequality for k equals 1, read k equals 2, it's 7 over 7, and 21 over 21, which is 7 choose 2 divided by 7 choose 2, and 28 over 35, which is 7 choose 3, and 7 less than that. And it's 1, 1, and something less than 1. But, I mean, what would be an intuition to get the convexity like this? The original intuition comes from the fact that the rank function of the matroid, well, the minus of that, is actually a convex function in the sense of discrete convex analysis. And we had some general understanding of how such discrete convex functions would give strongly log concave polynomials by using this tropical point of view. And then that would give this. So again, nowadays, it is completely natural for a human being to feel the desire that whenever your friends present their theorem that they are very proud of, you want to make a remark of kind like, oh, but that's the special case when the morphism, target of the morphism is a point, or something like that. So we are going to try to do that to this using our notion of morphism. And it fits in very nicely with this hunt for the notion of discrete convexity. And it tells you why these morphisms are really convex objects. let me make a quick definition. So let's say that a subset S of M is a basis of a morphism phi from M to N if S is in a basis of M and phi S contains a basis of N. So in other words, I want S to be independent in the source and spanning in the target. And the theorem we get with Chris is that for any such morphism M to N, we have 1 fk of a phi square divided by m choose k square is larger than fk minus 1 phi m choose k minus 1 fk plus 1 phi m choose k plus 1, where fk stands for the number of bases of phi of cardinality k. Okay. And 2, if you sum over all bases of phi of the monomials w0 to the m minus cardinality of s to the w of s, so this homogeneous polynomial has degree m and the number of variables is m plus 1. And this is Lorentzian, or strongly log concave. And we derive this in basically the same way. So what implies such a result is that for any parameters, and now there are 2 of them, p and q, both in between 0 and 1, what you would call Potts model partition function of a morphism, where the sum is again over all subsets of S, not just bases. And the monomial is p to the minus rank m of a S and q to the minus rank of a n of a phi S. And you have a monomial w0 to the m minus s and w to the s is Lorentzian. And you get this polynomial as a normalized limit of this polynomial. Therefore, this implies that. And once you have this, you identify all the variables in W with each other to get a bivariate homogeneous Lorentzian polynomial whose coefficients are exactly fk. So 3 implies 2 implies 1. Yes.
So if S is just identity map,
Yes.
then only one of these numbers is non-zero.
That's right.
And everything else is 0.
That's right.
So I guess you need to assume that the left-hand side is non-zero. Oh, okay,
Yeah.
yeah.
Yeah. 0, 0, 0, 1, 0, 0 is log concave. Yeah. So, well, when the target is a point, and what we mean by a point, it should be a final object, so it's a matroid on one element whose only basis is empty set, to which every matroid maps to. Then the second condition defining the basis of phi always holds. So you are really counting independent sets in this case. So 1 to 3 specializes to 1 to 3 in the previous case. That's it. Well, of course, this is a much more flexible notion. For example, if you apply this to this one, I have one matroid and another matroid, and then F I get is something like 0, 0, 27, 79, 111, 75, 0, 0, 0, 0. And you can compute these numbers by hand. It's not too painful. And the assertion is that if you divide this sequence by 9, choose k, where k ranges from 0 to 9, because there are 9 edges in the domain graph, then you get that logarithmic concavity. Yes, you would like to call it Todd polynomial for Coxeter matroids. Okay, so what is happening here? So let's just consider the special case of the assertion when P is equal to Q. Then this expression specializes to more familiar looking expression that we have discussed while we were talking about discrete convex functions. So it's like a Q to the minus rank of a M of a S. And maybe let's say phi is identity on ground set. So let's say then I'm adding that with the minus of the rank function of S. And I have the usual expression. And you see this discrete function defined on the Boolean algebra of M. And again, the key motivation to look for proof of such statement is the observation that this function is an M-convex function. And it's not too hard to convince yourself that once you get acquainted with the notion of M-convexity. But it is there's something subtle happening here. Because the rank function of a matroid is an M-convex function. I have another M-convex function. It is not true that the sum of convex function is convex. And this is the main difference between the continuous world and the discrete world. And this is also highlights the difference between the behavior of M-convex sets and M-convex functions. Whenever you have two M-convex sets, their sum is also M-convex. This is a shadow of the fact that the product of two Lorentzian polynomial is Lorentzian. But the same doesn't hold for M-convex functions. But in this case, it does, because there is a map from M to N. So what makes this convexity possible is the fact that the identity map on the ground set is actually a morphism from M to N. And this translates to M convexity if you play with it for a while. Okay. So the identity being a morphism It is what's called the concordance condition in this book, Coxa Matroids, by Borovich, Gelfand, and White. They say that M and N are concordant. And what they show is that a Coxa matroid of type A is really just a sequence of concordant matroids. At least in type A. And it is very easy, in a sense, to define what Coxa matroids are. According to one of their many definitions, they are just generalized permutohedras of that type with the property that if you look at the group generated by the reflections across the midpoints of every edge in your generalized permutohedra, then it generates a finite group. So it's a special type of polytopes. And in type A, such polytop contains exactly the same kind of information that a list of concordant matroids contains. You can somehow anticipate the need for such concordance condition by recalling our previous discussion. I mean, the point is that the sum of two convex functions is not convex in discrete setting. And remember how we tropicalized the space of Lorentzian polynomials with some valued and ordered field, K. And the typical picture we get is a tropical variety which somehow looks like this. It's the case when degree is 2 and variables is 5. So if you have one convex function here and maybe another convex function here, and then the sum will also convex. But if you're adding one convex function here with something in here, then you will probably end up outside of your tropical variety of convex functions. So to summarize, whatever Potts model or multivariate Todd polynomial, I'm not even sure it should be a polynomial, let's say Todd function of a Coxa matroid in a given type must be it should satisfy the analytic condition in that type. Let me show you another, this time even more obvious example that governs Koska numbers and Schur polynomials. So these are super classical concepts defined sometime in the late 19th century. Let me remind you. So it starts from a partition. So let's say I have a sequence of non-negative integers, maybe n of them. A partition. And let's view this as a so-called Young diagram, which is a collection of boxes with lambda 1 boxes in the first row, lambda 2 boxes in the second, and so on. And then we're going to fill in these boxes using alphabets. And define a semi-standard Young tableau say of shape lambda is obtained by filling in boxes of the lambda by alphabets from n, so that the entries weakly increases along rows and strictly increases along columns. And then you define the sure polynomial of lambda by saying that it is a polynomial in n variables, which is obtained by summing over all semi-standard Young tableau of shape lambda, where the monomial corresponding to given semi-standard Young tableau T is obtained by multiplying all the variables corresponding to the entries of its boxes. If you rewrite this in more standard form, summing over alpha, as we always do, then you get certain coefficients, and these are what are called Koska numbers.
X is W there? Are they the same thing?
Yeah. Oh, good point. So people usually use X. I have been using W throughout, so I was just trying to be consistent. Yes.
Can I go back to a statement you said before? So do you mean when you said that it's an M-convex function, do you really mean with two minus sign?
Yes.
But the domain is actually, so the domain is the same. So
Yes.
in the condition for the M-convex function, you just have this inequality on when you do, so like some modularity inequality. And so if the domain is the same, the sum would also be. So don't you mean that one of them is a plus? Because if you lift the other black bond, if you lift that black bond.
No, I don't think the condition defining M convexity can be additive. There are lots of quantifiers there. For any given I, there should exist J so that the inequality holds. But for given I, the J satisfying the condition for M and N may be different. And this is what causes the failure of additivity. Okay. Okay, so let's quickly do one example. So when lambda is the partition 2, 1, 0, then the Young tableau of shape lambda there are not that many. I should strictly increase along columns, so I should have a 1, 2, and 1, and 1, 2, and 2, and 1, 2, and 3. And I could have 1, 3, and 1, 1, 3, and 2, and 1, 3, and 3. And I could have a 2, 3, and 2, and 2, 3, and 3. So I have a 1, 2, 3, 4, 5, 6, 7, 8. So that if I sum over all these monomials, 8 monomials, then I get cubic form in 3 variables. So that if I draw this polynomial in the triangle of cubic forms, here's my cubes, then I get a hexagon. Where I have a 1 monomial on the boundary, but I have 2 in the center because I have W1, W2, W2, 3 here, and W1, W2, W3 here. And the theorem with Methan, Mazaros, and Saint Dizier, is what you expect. So for any lambda, well, to write the consequences first, you must have this logarithmic concavity of Koska numbers. Where I'm fixing lambda. For any I and any I and j, alpha and I and j. And correspondingly, if you define the normalized Schur polynomial as an exponential generating function for Young tableaus rather than the usual generating function, so you have a sum over alpha of a Koska number k alpha and w alpha to the alpha factorial is Lorentzian. In particular, it's low concave on the positive orthant.
So just to clarify,
Yeah.
exponential generating function, but you have a usual Schur function. Usual Schur function is written as a non-exponential generating function.
What's the
So
question?
just question about this alpha, where this alpha factorial is coming from. If you raise alpha factorial, also get Schur function.
This is not a Schur function.
So that's the question. That's not a Schur function, right?
Yeah, I put the underline here.
Oh, that's a new
Yeah.
function.
Yeah. Okay. So, combinatorially speaking, it's a rather explicit assertion. So, if my alpha is here, if I yes, so for fixed lambda, yeah. So there's lambda everywhere. Yeah. Here, 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 here. So if I start from pictures like this and start from any point alpha and move in any one of these root directions, I'm saying that 2 squared is larger than 1 times 1. So the number of ways to fill in the given Young diagram using letters 1 to 3 should be, if you square it, it should be always larger than the product of the number of ways to fill in with 1, 1, 2, and 2, 3, 3, for example. Okay, so of all the things that I have said this week, this is the only statement that is hard to prove for me at the moment. But it is also one of the most concrete assertions, so it seems ridiculous that it's not so, it cannot be done in the way that other statements were done, but at the moment, I don't see how to approach it. So in the end, how we prove this inequality is, of course, by showing that a certain polynomial is Lorentzian, but how do you show that is Lorentzian? The only way we see right now is to use the Hodge-Riemann relations for complex projective varieties that we construct from lambda, which is not Schubert variety, and use the Hodge theory there. Okay. But I think this is a very attractive statement because it clearly suggests what we should test in other types. Because these sure polynomials are characters of finite dimensional irreducible representations of GLN. And we have a picture like this in all types. And it's clear what this inequality must be concerning weight multiplicities of irreducible representations. And it is absolutely crucial here, of course, that the representation is irreducible. Because if it's not irreducible, you can just sum many things up, and you can easily ruin any sort of a convexity. So it sort of reminds me of a geometric situation where you deal with perverse sheaves. I mean, if you just look at arbitrary of them, you don't see any sort of a convexity. But once you decompose it into simple pieces, at least in complex geometry, you start seeing these Hodge-Riemann relations, which are responsible for lots of these convexities that we have been seeing. I mean, it could be theoretically that all Lorentzian polynomials come from such structures. But our proof right now is very ad hoc, and it's not very pretty. So one question would be, do we have such convexity results for irreducible, finite dimensional irreducible representation in other types? And maybe also, even in type A, if you look at highest weight simple modules that are not necessarily finite dimensional, you can still ask whether you have a convexity, but I have no intuition and very little examples. So let's put it that way, and I'll stop here. Thanks.
Any questions, June?
Yep.
So for this inequality, is there a stronger conjectured version that where you put some denominators, like the one up there?
No. No. So, okay, so that's actually a very nice observation. So there is something funny happening here. If you really remember what was happening for discrete convex functions, this is the only instance where I'm not using exponential generating function. I'm not doing this. No. M minus S factorial. The Lorentzian property of this is clear if you accept the convexity of the exponents. But what is amazing about matroids and Coxeter matroids in general is that their rank functions are so convex that I can even omit this. If you just prove the weaker, the automatic version with the normalized exponent, then you get the certain version of log concavity of the number of independent sets, for example, and that is exactly what the Hodge theory of projective varieties of this, in this case, the wonderful model tells you. And what is interesting is that if you stick to that algebraic geometric setting, you can never go beyond this, and you have to just satisfy at that level. No. That is something special about matroids.
Any other question?
Yeah. So while you were talking about this, I found online old paper of Openpop which discusses this type of statement. So how is it related to?
Yeah.
I did not find that he proved this statement, but definitely he discussed very.
Yeah. So the paper you're looking at has the title, Why Would Multiplicities Be Log Concave?
Yeah.
So I looked at that paper and yeah, I don't know why multiplicities would be log concave. Yeah. But sometimes you can prove it.
So here's another paper which proves something. Maybe not for this particular problem.
Right. It's not weight multiplicity. He was more interested in this like a little Richardson coefficients and their convexity, which is not true in fact, but that's true.
So maybe I can also add a couple of comments. We have a paper with Lenin Piliatsky which might also be related to this. We put some conjectures of Kunkov. But I have another question or comment, is that there is a continuous version, I guess, of this inequality. If you dilate lambda, then you get a measure on this polytope, which is called Duster-Heckman measure,
Yes. Yeah.
which is, I guess, known to be log concave. So that can be thought as discrete version of this.
So what we are doing to prove this inequality feels very similar. So we have to construct a variety so that these are sort of intersection numbers of positive line bundles, and then we win. We just apply Hodge-Index theorem, and then we win. But what we thought initially would do the job didn't do the job, so we had to do some dirty works.
So is this statement for the measure known for all types?
I know it probably, but I don't know.
I think so. You have that, the other Victor.
If you apply this strategy to Schubert varieties, or honest Schubert varieties, you get the Lorentzian property of that polynomial that appears in paper of Posnikov and Stanley, which has something to do with counting chains in Brouillard order. That is also Lorentzian.